Welcome to this lecture on the history of artificial intelligence. To understand the current state of artificial intelligence, it is essential to examine how the field has evolved over time and the key ideas that have shaped its development. We will explore the major milestones in the history of artificial intelligence, highlighting important breakthroughs as well as periods of slower progress. We will also introduce the main approaches to artificial intelligence, discussing how different paradigms have attempted to create intelligent systems, as well as the different types of artificial intelligence, and consider how these categories help us understand both the capabilities and future direction of artificial intelligence. The origins of artificial intelligence are closely linked to the emergence of modern computing during the 1940s and 1950s. Although artificial intelligence had not yet become a distinct field, the theoretical and technological foundations that made it possible were established during this period. A key milestone occurred in 1936, when Alan Turing introduced the concept of the Turing machine, a mathematical model capable of describing any computation that could be performed algorithmically. This concept provided a theoretical framework for understanding computation and became the foundation of computer science. Turing also proposed the idea of the universal Turing machine, which demonstrated that a single machine could execute any computable algorithm given the appropriate instructions. These theoretical ideas were later realized in physical computers such as ENIAC, one of the first general-purpose electronic computers. Another major breakthrough came in 1945, when John von Neumann described the stored program computer architecture. In this design, both program instructions and data are stored in the computer's memory, allowing programs to be modified and executed efficiently. The von Neumann architecture became the standard design for most modern computers and remains highly influential today. Together, Turing's theoretical work and the development of early computers established the computational foundation upon which artificial intelligence would later emerge. The concept of a Turing machine, and later the computer, is based on the idea of a machine that follows precise instructions, or algorithms. Everything a computer does is determined by a sequence of rules that tell it exactly how to process information. If we provide decision rules, such as if-else statements, a computer can make choices based on the input it receives. Although these decisions may appear intelligent, the computer is simply following the instructions it has been given. Computers can also learn, but only if they are provided with learning algorithms that specify how they should improve their performance from experience. This idea later became the foundation of machine learning, one of the most important branches of modern artificial intelligence. Another key advantage of computers is their speed, as they can execute billions of instructions every second while producing highly reliable results. When correctly programmed, computers rarely make mistakes because they perform computations consistently and without fatigue. In the early days of computing, these capabilities led many people to describe computers as electronic brains. Since computers could process information much faster than humans, researchers began to wonder whether they might eventually be capable of intelligent behavior. The figure on the right illustrates the basic logic of a Turing machine. It shows different machine states, such as S0 and S1, and how the machine follows specific rules depending on the symbol it reads on the tape. For each step, the machine reads a symbol, writes a new symbol, moves left or right, changes its internal state, and continues until it reaches a halt state. This simple rule-based model of computation laid the foundation for the earliest approaches to artificial intelligence, which assumed that intelligence could be modeled as symbolic computation carried out through explicit algorithms. The development of the first computers raised an important question in both science and philosophy. Can computers think? As early machines became more capable, researchers began to question whether computational systems could be considered intelligent in any meaningful sense. In 1950, Alan Turing proposed a way to approach this question indirectly. Instead of defining what thinking is, he suggested evaluating whether a machine could imitate human behavior well enough to be indistinguishable from a human in conversation. This idea became known as the Turing test, where a human judge interacts with a machine through text-based communication. The goal is to determine whether the responses come from a human or a machine without knowing which is which. The key concept of the Turing test is that intelligence is defined through behavior rather than internal mental states. A machine is considered intelligent if its behavior cannot be distinguished from that of a human in a text-based interaction. In this view, it is not necessary to decide whether the machine is conscious or truly thinking in a human sense. Instead, what matters is whether it can produce responses that are functionally equivalent to human communication. This shifts the focus of intelligence from internal processes to observable performance. Despite its influence, the Turing test has several important limitations. One major criticism is that it does not require true understanding from the machine, only the ability to produce convincing responses. This issue is highlighted by John Searle's Chinese room argument, which shows how a system could follow rules to manipulate symbols without actually understanding their meaning. Another limitation is that the test focuses only on verbal and linguistic abilities. As a result, it does not evaluate other important aspects of intelligence such as perception, physical interaction with the environment, creativity, or real-world problem-solving. This figure illustrates a simplified timeline of artificial intelligence research, showing how the field has developed through several distinct phases over time. Each colored curve represents a different wave of artificial intelligence development, where new ideas emerge, gain momentum, and eventually decline or transform into new approaches. This pattern reflects the fact that AI has not developed in a straight line, but rather through cycles of rapid progress, followed by periods of slower development. The earlier phases represent foundational approaches, where symbolic and rule-based methods were dominant. These approaches focused on explicitly programmed logic and structured representations of knowledge. As time progresses, we see additional waves that reflect shifts in methodology, particularly the move towards statistical and data-driven approaches. The overlapping nature of the curves shows that new paradigms do not completely replace earlier ones. Instead, they often build upon or coexist with previous methods. This cumulative development is an important feature of artificial intelligence research. The final rising curve represents the most recent phase of artificial intelligence, which is characterized by sustained growth and increasing performance. This progress is largely driven by advances in computational power, the availability of large datasets, and modern machine learning techniques. Overall, the figure highlights that artificial intelligence development is best understood as a series of evolving paradigms rather than a single continuous trajectory. The first wave, highlighted in blue, represents symbolic artificial intelligence and which is the initial paradigm of artificial intelligence, where systems are built on explicit knowledge representation, logic, and rule-based reasoning. This approach focuses on structured symbols and human-defined rules to model intelligent behavior. In the following sections, the presentation will concentrate on this paradigm in greater detail. The first period of artificial intelligence is symbolic artificial intelligence, often described as the field's first artificial intelligence summer, a time of strong optimism and rapid theoretical development. It spans from 1956 to the early 1970s and began with the Dartmouth Summer Research Project in 1956, where John McCarthy introduced the term artificial intelligence. During this period, researchers were guided by a central question: can machines think and reason like humans? This question shaped much of the early direction of the field and led to the development of symbolic approaches based on logic and rule-based reasoning. Symbolic artificial intelligence is based on the idea that intelligence can be achieved through explicit reasoning and structured knowledge. The main goal was to reproduce human-like thinking by representing information in a formal way and applying logical rules to it. Instead of learning from data, as modern artificial intelligence systems often do, Symbolic artificial intelligence systems work by manipulating symbols that stand for objects, ideas, and relationships. These symbols are processed using rule-based logic, often written as if-then statements, which guide the system's reasoning. Another important technique used in this period was search. When solving a problem, the system would explore different possible steps one by one until it found a solution. To make this manageable, researchers often use simplified environments called microworlds, where only a small number of objects and rules existed. Several early systems demonstrate these ideas in practice. ELIZA showed how simple rule-based patterns could simulate conversation. SHARDLU could understand and manipulate objects in a virtual blocks world using language. And Shaky the robot combined perception and reasoning to perform simple tasks in a controlled environment. Together, these systems reflect the core belief of symbolic artificial intelligence. That is, that intelligent behavior can be achieved by encoding knowledge as symbols and applying logical rules to manipulate them. To better understand how symbolic artificial intelligence works, let us use chess as an example. Chess was one of the classic problems studied in early artificial intelligence because it requires logical reasoning and planning rather than learning from data. The first building block is symbols, which represent knowledge about the world. In chess, symbols describe the current state of the game, such as where each piece is located. For example, we might represent the fact that the white queen is on d1 and the black pawn is on e5. We can also represent actions, such as moving a piece from one square to another or removing a captured piece. The second building block is rules. These are explicit if-then statements that tell the system how to reason. For instance, if the queen moves from d1 to e5, then the pawn on e5 is removed. Instead of learning this behavior from examples, the rule is explicitly programmed into the system. The final building block is search. In a game of chess, there are many possible moves, so the artificial intelligence must systematically explore different alternatives before deciding on the best one. It does this by generating all legal moves, considering how the opponent might respond, removing branches that are unlikely to lead to a good outcome, and finally, selecting the move with the best expected result. This example highlights the fundamental idea behind symbolic artificial intelligence. Intelligence is achieved by combining stored knowledge, represented as symbols, with logical rules and systematic search. Rather than learning patterns from data, the system relies on explicit reasoning to solve problems. This example illustrates how symbolic artificial intelligence works in practice by looking at one of the most well-known symbolic artificial intelligence systems, SHARDLU. SHARDLU operated in a simulated environment called the blocks world, where it could interact with a small set of colored blocks using natural language commands. The key idea behind SHARDLU was to demonstrate how intelligent behavior could be achieved by combining structured knowledge with logical reasoning. Instead of learning from data, the system relied on explicit representations of its environment and predefined rules. First, SHARDLU represented its environment using symbols. These symbols were stored as formal facts that described the current state of the world. For example, facts such as on block A, table, or color block A. Red specify where objects are located and what properties they have. Together, these facts formed SHARDLU's internal world model, allowing the system to keep track of its environment. Next, SHARDLU used logical if-then rules to determine which actions were possible. For example, a rule might state that if a block is clear, meaning that no other block is on top of it, and the robot hand is empty, then the block can be picked up. These rules enabled the system to reason about its actions before carrying them out. On the right side of the slide, you can see an example of this reasoning process. When the user gives the command "pick up the red block," SHARDLU first searches its internal world model to identify which block matches the description. It then checks whether all the necessary conditions are satisfied by applying its logical rules. If the block is clear and the robot hand is available, the action is executed, and the system updates its internal representation to reflect the new state of the world. This example demonstrates the fundamental principle of symbolic artificial intelligence. That is, intelligent behavior is achieved through explicit knowledge representation and logic-based reasoning, rather than by learning patterns from large amounts of data. In this slide, we look at the key features and limitations of the SHAR-DLU system. First, SHAR-DLU showed several notable capabilities. It could understand simple natural language by translating human instructions into formal symbolic representations that the system could process. This meant that users could interact with it using everyday language, at least within a limited domain. In addition, SHAR-DLU was able to reason about objects and their relationships within its environment by applying logical, rule-based reasoning. Based on this internal model of the world, it could also perform planning, as it was able to determine a sequence of actions needed to achieve a given goal, updating its actions according to the current state of the environment. However, the system also had several important limitations. SHAR-DLU struggled with ambiguous language, since symbolic systems require precise and unambiguous interpretations of words and sentences. Even small variations in phrasing could lead to misunderstandings. Another key limitation was its heavy reliance on hand-coded rules. In other words, its so-called intelligence was not learned from data or experience, but instead explicitly programmed by humans, which made it inflexible and difficult to scale. Finally, SHAR-DLU was confined to a very restricted simulated environment known as Block's World. As a result, it could not transfer its abilities to real-world settings, where complexity and uncertainty are much greater. On the right side of the slide, you can see a demonstration of SHAR-DLU in action, showing how it interacts within its simulated environment. In summary, SHAR-DLU represents an important early milestone in natural language understanding and reasoning. At the same time, it clearly illustrates the strengths and fundamental limitations of symbolic artificial intelligence approaches, particularly their difficulty in scaling beyond controlled, artificial environments.